Question 17, 2011, Paper 1 Higher Maths. We have a cubic curve and we're asked what the equation of this cubic curve is. I'm going to take you through two different methods of doing this. The first method is, in a sense, it's quite limited. It relies on the fact that you have possibilities for the equation given to you. The second method is a lot more general, more sophisticated. So let's have a look at the choices that are given. Here they are, the four possibilities for the equation. Now, the method we're going to use relies on the relationship between the formula for this curve and the points on this curve. Every single point on this curve, the two coordinates of the point, the x value and the y value, have to satisfy the equation of the curve. That's the relationship between the equation and the curve. For instance, if we have a simple example where, for instance, y equals 2x, which we know is a linear equation, that means its graph is a straight line. Every single point on this graph, for instance, the point 1, 2, where x is 1 and y equals 2, satisfies this equation. When we put x equals 1 in there, twice 1 is 2, we get the y coordinate 2. There's the point 1/2, 1. It lies on the straight line. If we replace x by a half, twice a half is 1, there's the y value. If we go round to -2, -4, which lies on this curve, if we replace x by -2, twice -2 is -4, and there's the y coordinate. So every single point on this graph, the coordinate values satisfy this equation. That's the relationship between the equation of a graph and the points on the graph. So let me just clear that and go back and consider this point. We know the coordinate values for this point, and we know the point lies on the curve. The point is -1, 0. The x value is -1. The y value is 0. Now, we can go through each one of these potential equations for this graph and substitute these values in and see if they work. If they don't work, this won't be the equation of that curve. So let's try and substitute x equals -1 into this equation. So minus minus 1 is 1, -1 plus 1 is 0, -1 minus 2 is 3. We've got 1 times 0 times -3. That just gives us 0. Y equals 0. So that point, the values of its coordinates satisfy this equation. So this could potentially be the equation of this curve. Let's check this, or these values, in the second possible equation of the curve. So x equals -1, we'll try it in here. Minus minus 1 is 1. -1 minus 1 is -2. So that's 1 times -2. -1 plus 2 is 1. So that's certainly not going to give us 0. 1 times -2 times 1 does not give us 0. So there is no way that this equation can be the equation of this curve, because this point would not lie on it. Let's try the third one. X equals -1. We've put -1 in there, we get -1. We get 0 in there. -1 plus 1 is 0. -1 minus 2 is -3. So that certainly comes to 0. -1 times 0 times -3 does give us 0. So this again is a potential formula for this graph. Let's try the fourth one with x equals minus 1. If we put minus 1 in place of x here, substitute in minus 1 times minus 2 times 1. That's certainly not 0. And we're supposed to have y equals 0. So this formula can't possibly be the formula for this graph, because these values do not satisfy this equation. And we certainly know that the point that has these values for its coordinates lies on the curve. So that's not a possible formula. Let's move on to this point, 0, 0, which certainly lies on the curve, x equals 0, and y equals 0. Now, because every formula has x multiplying by x, and because we're putting x equals 0 in, it doesn't matter what value these take, the whole result on each of these will be 0. So this point certainly lies on all these curves, whatever they are. So this point is not eliminating any more of these. This point certainly lies on this one and this one. So let's now go to this one. This is the point 2, 0. X equals 2, y equals 0. So let's substitute x equals 2 in here. Get minus 2, 3, 0. So when we multiply these two, we certainly do get 0. These three values, we certainly do get 0. So that's a potential formula for this curve. We don't need to bother about this one and this one. So let's try choice C, replacing x by 2. 2 times 3 times 0. Again, that's 0. So this is another potential formula for the curve. So we'll have to look at this last point where x equals 1 and y equals 2. And let's hope that this one can distinguish between these 2 points, these 2 choices. So let's substitute x equals 1 into this one. We get minus 1 times 2 times minus 1. Well, minus 1 times 2 is minus 2, times minus 1 gives us 2, which is what we're supposed to do. Now let's just check that for this equation, these values do not satisfy the equation, and therefore this cannot be the equation for this curve. So putting x equals 1 in here, we get 1 times 2 times minus 1. Well, that gives us minus 2, which is not what we're trying to get. We're trying to get a y equals 2 out of this. So that leaves us choice A as the correct choice. But you'll notice in that method we had to be presented with potential formulae, and we had to check that the various pairs of values of the coordinates worked in there. So that method would not work, for instance, in a written non-multiple choice question. So we'll need to look at a different method of solving this. So here we are with a cubic, no possible equations given for it. We have to try and figure out what its formula is. Now, this method relies on the fact that if you did have a formula involving x's and so on, and you asked when the heights on the curve were 0, in other words, as y equals whatever it is involving x, we usually put some formula involving x, f of x, function of x. So there's a whole expression here involving x, and we're asking when on the graph are the heights 0. In other words, there. There are 3 places in this one. Now what normally happens is that you try and factorize this, produce a factor, another factor, another factor for instance, and therefore this one will be equal to 0, or this one's equal to 0, or this one equals to 0. And therefore you get your value for x. This is precisely the points where the curve crosses the x-axis. So if we take this one, we're supposed to be getting out an x equals minus 1. That would come if we had an x plus 1. So one of the factors in there should be an x plus 1. This one, we're supposed to just get an x equals 0, so that would just be an x. There'd be no problem with that one. This one, we're trying to get an x equals 2 out of the thing. Sorry, I shouldn't have put that there. X equals 2. This would therefore come from an x minus 2 equals 0. So there's x minus 2. So it would appear that the formula for this curve is y equals, and it's the product of these 3 factors, one coming from each of the points where the curve crosses the x-axis. Let me put just the x at the front. Then there's an x plus 1, and then there's an x minus 2. That would be fine, however there is a problem with that. There are a host of curves that can be drawn, cubic curves that can be drawn so that they cross the x-axis at these 3 points. I've drawn another one where there's a scaling along the y-axis. Instead of a height of 2, we could have a height of 4 there. Instead of this little height, we could have that height down there. This would involve doubling heights. So some sort of multiplying by a constant in here, a scaling factor, would have to be introduced. And on this curve, the only way we can tell what that scaling factor is by examining this point 1, 2. All the other points have a height of 0, and each of these factors is tied to one of these, so there's nothing in the information from these 3 points that tells us what the scaling factor could be. Only the point 1, 2 would give a clue as to what the scaling is. X equals 1 and y equals 2. So at this stage we have to substitute 2 for y. We don't know this scaling factor. X we're saying is 1 from this point. 1 plus 1 is 2, and 1 minus 2 is minus 1. So let's just continue this down here. So we've got 2 on the left, k times 1 times 2 is 2, 2 times minus 1 is minus 2, so it's k times minus 2. And that would presumably mean that k is minus 1, because minus 1 times minus 2 gives you positive 2. Or divide both sides by minus 2. 2 divided by minus 2 will give you minus 1. So the scaling factor is minus 1. So we've ended up producing an equation which has a minus 1 times x, that's just written as minus x, and 2 factors, x plus 1 times x minus 2. Now I can't at this stage remember which order these were multiplied, but it doesn't matter. The order of multiplying 2 things is not important. So I can now check choices, and there they are. I did get the order right. But that's choice A as we had in the original solution. So choice A. So factor method, where each factor there is tied to an x-axis intercept of the curve, and a scaling factor at the front where you need a point that's off the x-axis. Here again is the graph from the question, this time with a set of sliders, just to illustrate some of the points I was talking about. The formula of this graph looks quite complicated, but we have values for A, B, C and D up here. The value for A is -1. That's the scaling factor. B has value -1. So this factor is x minus -1, which is x plus 1. And remember that factor went with this point of intersection with the x-axis. C has a value 0, so this factor is x minus 0, which is just x, and that factor went with this point of intersection with the x-axis. D is 2, so this last factor is x minus 2, and this factor went with this x-axis intercept on the graph. So these three factors involving x correspond to the 3 points of intersection of the graph with the x-axis intercepts as we call them. And this value A is the scaling factor. Now I can illustrate why it's called a scaling factor along the y-axis. If I change its value, let me change it to -2, and you notice the heights have increased all the way along the graph, even more so, value -4 and so on. So multiplying all the heights by -1 by 0, that's now not a cubic graph. That's the graph y equals 0, which is just mainly the x-axis. Multiplying by 1, the whole graph from -1 has now been flipped in the x-axis. The heights have been multiplied by -1 compared to the previous one. So it's flipped in the x-axis. And then they're doubled in heights, trebled, multiplied by 4, multiplied by 5, etc. So let's go back to the original -1. There's the original graph. And let's concentrate on this factor x plus 1, or x minus -1. And let's change this to -2, so that this factor is now going to be x plus 2. The graph now crosses at -2. It used to cross at -1. This is not now an x plus 1, this is an x plus 2. The other 2 points of intersections, the ones that go with x minus c and x minus d, have not been altered. They're still 0 and 2. These values are still 0 and 2. But it's the b value that's now gone to -2 with the factor x minus -2, which is x plus 2. That's moved along, and if we continue altering this, we can move it to -3. There's the intersection moved along to -30. The other two have remained the same. So let's now move it back to where we had it, and let's try and move this along to there. So we should really have a factor of x minus 1. So if we increased c to a value of 1, there it is. It's moved from there to there. The 2 is exactly the same. The -1 corresponds to this is exactly the same. So let's move that back again to 0. I've got the wrong one. That's this one. Let's move it back to 0. There we go. And let's try and move this along to 3. So this would become x minus 3. D would have to increase to 3. And there it is. We've moved this along. The other 2 intersections that go with B and C there have not been changed. So that's, I don't know if that helps, but it might help. It's a more dynamic way of looking at the graph.